Okay, now where were we? Okay, let's recall a few things about K theory. Well, first of all, if we have a cumulative monoid with zero, there is a way to construct an abelian group starting from this monoid. Now, well, this construction has this construction is basically comes equipped with a map of with the map of monoids, and this map is the initial object of the category of maps of monoids from M to an abelian group. Now, does any of this make sense?
Could you recall what is a monoid?
Well, a monoid is a group without inverses.
Mm-hmm.
Let's write this. Let's write it in quotation marks. Well, there's no such thing as a group without inverses, but if we have all axioms of a group except for the inverse axiom, then the resulting object is called a monoid. For example, Z greater than or equal 0 is a commutative monoid.
Okay, it is clear. And what is K of M?
Is a commutative monoid with 0, and K in this case is equal to Z, just to Z. So well, K of M is the set of formal differences M minus N, where M, N are in in the monoid with the following equivalence relation: m1 minus m1 is equivalent to m2 minus m2 if and only if there is a k inside m such that m1 plus m2 plus k is m2 plus n1 plus k.
Okay, so that K of M is a group and K is a functor from the category of monoids to abelian groups.
Yes, and moreover, this functor is well. Let's see. So we have a forgetful functor from abelian groups to commutative monoids. Hold on, something happened. I don't know what this is. Close. Okay. So there is a functor from there is a forgetful functor from abelian groups to commutative monoids. And this functor is adjoint to the k functor. But let's see whether or not it's adjoint on the right or on the left. First of all, place your bets. Is it right or left? Well,
forgetful functors are usually right adjoints.
Well, okay, let's see. So we have mon or cmon. Something, which is isomorphic to something. Well, let's see. So we have what do we know? We know that the map of abelian groups from Km to G are the same as maps of monoids from M to F of G. Okay, well, so indeed, K is the left adjoint and F is the right adjoint. Okay, well, we'll not need this absolutely, but it's useful. It's useful to know. Anyway, we have this this construction, which can also be made very explicit as follows. We just take all formal differences with this equivalence relation. Okay, well, let's now take m equal vect x for x a finite CW complex. What is vector x? Well, let's say that this is the set of isomorphism classes of okay, let's put a k here and say that the set of we consider the set of isomorphism classes of k vector bundles. K is R or C or or could or as well consider vector bundles with some other structure, some vector form or something. Now, we apply this K group procedure and get a monoid which would denote K R of X or K C of X and most of the time we will be considering the complex K theory. So unless it says R, all vector bundles will be complex. Okay, now there is a slightly different group. Which I denote K tilde of X, which is the set of stable equivalence classes.
And the operation in M is just a witness sum.
Yes.
Witness sum.
The operation is the witness sum or the direct sum of vector bundles. So what is a stable equivalence class? Okay. Let me give the following definition. So the stable equivalence is generated by is the equivalence relation generated by adding epsilon 1. where epsilon1 is the trivial bundle of rank 1. Okay. Now, what's the relation between the real and complex no, between the groups with the tilde and the groups without the tilde? Let's see. So first of all, I have a map from K without the tilde to K tilde. No, sorry. Well, this map is pretty straightforward. We just take a vector bundle with respect to one equivalence relation to a vector bundle the same one with respect to the other equivalence relation. Now, using the universal property of K without the tilde, we get a well-defined map of abelian groups. But there's one thing which I didn't mention. Why is K tilde a group? Well, here we use the fact that X is compact.
Could you repeat what is the equivalence relation in K tilde?
Well, the equivalence relation is generated by adding a copy of the trivial bundle of rank 1.
So two vector bundles are isomorphic if they are isomorphic after adding
some copy to each, some copy of the trivial bundle to each of them. Yes.
What means some copy?
Say again.
In what sense some copies? So we can just
well, if the bundles have different rank, then we have to add different numbers of copies to get isomorphic bundles. For example, we know that the tangent bundle to the n sphere plus one copy of the trivial bundle is trivial. So the tangent bundle of the n sphere is stably trivial, which means if we take one copy and add it to one copy of the trivial bundle and add it to the tangent bundle, we get the trivial bundle. And for the zero bundle, we have to take n plus one copies of the trivial bundle to get an isomorphic bundle.
Okay, now it is clear.
Okay, so we need to prove that this is a group, and this follows from the following construction. For every e, okay, a vector bundle, there is an e prime x which is another k vector bundle such that e plus e prime is trivial. Well, does everyone understand how to prove this? Okay, let's prove this. Let's first prove this for the tautological bundle. Well, for the tautological bundle, we have this formula. Basically, the tautological bundle plus the orthogonal complement with respect to some Euclidean or Hermitian metric is the trivial bundle of rank m, where m is well, m is the dimension of the vector space, the Grossmanian of which we take. Does this make any sense?
Yes.
Okay. Well, and then we use the fact that over a compact X, every vector bundle is induced by a gamma nm. Every vector bundle of rank m, no, rank n, is induced from the tautological bundle over some finite Grossmanian. Well, for infinite x, we may have to use the infinite Grossmanian, but for finite for compact x, we don't need to. A finite one would do. Okay, so now we know that for every bundle there is a complementary bundle, and this means that for every element of k tilde there is an inverse, and such that the sum is stably trivial, which means stably equivalent to the zero bundle. Okay, so now we know that k tilde is a group. Does everyone agree?
Yes.
Okay. Well, Leonard agrees, and nobody disagrees, which is a good sign. Okay. Now we have constructed a map from k to k tilde. Let's construct a map in the opposite direction. We're running out of time again. Never mind. So k tilde k of x to k of x. Well, let me take the stable equivalence clause of a bundle E, and take it to the bundle E minus epsilon to the rank of E. And well, it's straightforward to see that if two bundles are stable equivalent, meaning if I add a copy of epsilon 1 to E, well, I get E plus epsilon 1 here, and epsilon blah 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 plus 1 here, and this is the same element in the K group. So the map is well defined. Now, what happens if I apply this map first, and then this map? Well, I get the identity. What is the kernel of this map? From k without the tilde to k with the tilde. Well, let's write it here. In other words, suppose I have suppose I have a vector bundle E1 minus E2. Suppose I have a formal difference of two isomorphism classes of vector bundles. Such that the vector bundles are stable equivalent. Well, what does this mean? This means that E1 plus epsilon L is isomorphic to E2 plus epsilon m. As vector bundles. So in the K group, we have no plus without the circle. So this means that in the K group we have E1 minus E2 minus the class of E2 is equal to plus or minus epsilon m minus n. Well, what does this mean? Well, this means that the kernel is generated by simply by the images of the trivial bundle and their inverses. And as a group, this thing is isomorphic to Z. So we have K of X isomorphic to K of X tilde plus Z. So the conclusion is there is well these two groups are closely related, and in some sense they are exactly the same up to this extra summand of Z, which basically corresponds to the rank of the bundle. Are there any questions? Well, we have 2 minutes left. Let's classify elements of what of K tilde of X. Well, my claim is that K tilde of X is isomorphic to what? To the set of homotopy classes of X to BU. What is BU? it's the direct limit of BUN. Now, does this make any sense? Okay, I'll save the notes until it's too late. Okay, I've saved the notes, and we'll reconnect in a minute, and then come back again to this question. Does everyone understand what BUN is, and which maps I take when I take the limit?